Okay, so last time we had begun proving some theorems about Dirichlet series. So one of the most useful results we had for these Dirichlet series, so we have this theta function, which we had determined that this theta function is actually this phi function just under a change of coordinates. So we just have the input of the sequence undergo an exponential change, and then we take the logarithm of the output, and then that's theta. We had a few other results. So in particular, this relationship between theta and phi, this lets us essentially take any of the results we had about phi and attempt to translate them over to the context of theta. So for example, one of the things we had was if these, oh, hello. So yeah, I'm just going back over what we had done previously. So we had defined this theta function for the use with Dirichlet series, and we had found this relationship between theta and phi, and we had shown that if we have two sequences where the sum of their theta value is defined, so that means we don't have an indeterminate form like infinity minus infinity. So long as this is the case, then the theta of their product is less than or equal to the sum of their theta values. And this follows from, essentially, it's the same property with phi, but instead of having the sum, we have a product. And the reason that the sum, the reason that we go from a product to a sum is essentially because we have this log on the outside. So we have theta of alpha beta, and we just have this little proof here. So we have this log of these sequences. This is less than or equal to, since logarithm is a strictly increasing function. This is less than or equal to the product of these phi values. That's the result from phi, and then we just separate these up. The log of the product is the sum of logs, and this is valid so long as the product is determinate, so it's not in indeterminate form. So as long as it's not infinity times 0, then this sum will also be defined. And then this is just using, again, the change of coordinates in reverse. This is just theta beta, and this one's theta alpha, and that gives us the result. We had done this one, this theorem here. I think that was the last complicated one that we did. Essentially, if we have any value s in the space A, then this sequence of exponentials e to the power of s times r, where r is a real number. If we take the phi value with r increasing towards infinity in the real line, then this has a phi value, and it's exactly e to the power of the real part of p1 of s. So this is sort of a generalization. Originally we had this, but for integer exponents, and now we have any real exponent. So you can sort of consider this as, instead of just doing s, e to the power of s r, you could consider this as e to the power of s, and then raised to the power of r. And so we had this result for essentially for if r is an integer, and if the base is any number, including a unit. But here we've extended to the case where the base is a unit, and the exponent is any real number, just going across real numbers. Proving that theorem about this allowed us to prove this corollary. So if we have this theta function applied to a sequence times n power s, we just end up with this. So essentially what this is saying is similar to the way that if we have phi of, if we have a phi value of some alpha times, phi to the power of n, then we would end up multiplying by phi. But here we're, instead of adding or multiplying by the absolute value of the p1 of phi, or whatever the base is, or x. But here it's similar. Instead of being the absolute value of p1 of x, is the real part of p1 of s. And we're adding instead of multiplying. Yes, so sort of the key thing to take away here is not only do we have this relationship like this, but also this sort of tells us what the theta function is doing in more intuitive sense, is that it's essentially attempting to approximate this alpha sequence in terms of these n power s terms, or rather n power theta. So I did some minor edits just before stream, and I made a note right here that for the sake of intuition, the theta value of this sequence n power theta, which is sort of like a polynomial term, is equal to theta for any real theta. By this corollary here, actually this applies for this does apply for any real theta, but you can sort of extend this to this more general case for any exponent that's in our space A, that this would generalize. Anyway, so yes, so that was essentially all we did, and we were working up right to here. So this is where we're now at. So the last thing we had done, the very last thing, was prove that if we have a summation of some alpha n's, this will converge if the theta value is less than -1, and it'll diverge if the theta value is greater than 0. So this is what we had just proven, and essentially this is a p-test. So we just use the third characterization to bound our alpha series by this, so just like this, a times n power theta, where a is some constant which is real on each index, and then we just sort of factor out this a by summing them all up, and we get absolute convergence. So that's nice. But what we actually want to do here with this is to not just have, when a summation like this will converge or diverge. Actually, we want it to be specifically in the context of Dirichlet series. And so that's a theorem we're working on here. So I've restructured this theorem a little bit from where it was when we left off. I've sort of merged two things into one, and we haven't done the second part yet. So the first part of this theorem is that this Dirichlet series, d of alpha, so alpha is the coefficient and s is the variable, this Dirichlet series will diverge if the real part of p1 of s is less than theta of alpha. So it'll diverge under that condition, but it'll converge and be analytic in the case that the real part of p1 of s is strictly greater than 1 plus theta of alpha. So what we had done last time is we solved the divergence convergence, so essentially just from this lemma and the fact that we have this little property here, where we can figure out the theta value of alpha n times n power s. Given these, we can get the convergence and divergence pretty much immediately from these two. So we just let beta n be equal to alpha n times n power negative s, and again, these are the terms that we're summing up when we're calculating the Dirichlet series. But if we have this, then the theta value of beta is just the theta of alpha minus the real part of p1 of s. That's from this first result. And this is relevant because the Dirichlet series of alpha with variable s is just this summation of beta n, which the convergence and divergence comes from the lemma. But the next thing we want to do is actually prove differentiability. So we actually want to show that for let me produce some words, hold on. We want to show that for s in this domain, so the real part of p1 of s greater than 1 plus theta alpha, that our function d alpha s converges, so we have convergence. We actually want to prove that it's differentiable, that it converges to actually an analytic function more specifically. So we're going to prove this. So in order to prove this, I think we're going to make use of this theorem 6.4. So to recap on what this theorem is, we'll scroll back up if I can find it. Perfect. Okay, 6.4. If we have a sequence of functions which are differentiable on a proper domain, then the sequence of functions converges, and the sequence converges compactly to the sublimit function, any function. Just we have compact convergence. Then the limit function is differentiable on this set S, on this proper domain. So we're going to use this result. So what we'll have to do for this is we're going to have to pick our functions. So we'll actually, for this, we'll just use the partial sums of the Dirichlet series. We're going to verify that all of them are differentiable on a proper domain, and then we're going to show that they converge compactly, and that will be our proof, so that we can conclude with differentiability. So write down here. So we're going to make use of 6.4. So first we'll notice, so we'll say let S be the set of lowercase s in A such that the real part of P1 of S is strictly greater than 1 plus theta of alpha. And then we can, so this is an open set, so it's going to be a proper domain immediately. So S is an open set, so it is also a proper domain. We haven't proven this condition. Actually, we haven't proven just about anything on what actually constitutes a proper domain. But suffice to say, since our space is locally convex, then all the open sets are locally convex. And since it is open, it's really easy to create a loop that encloses our function if it's an open set, which turns it into a proper domain. So we won't go through that proof, but we'll just have this essentially. We're just going to just sort of put this out there that an open set is always a proper domain. It's locally convex, and we can have all the loops that we want. Okay, so we'll let our function. So we'll let for each capital N in natural, let f sub n of S be defined as this summation, and we'll go from n equals 1 up to capital N of alpha sub n times n power minus s. And we'll just say this is, which is a differentiable, which is differentiable. Differentiable in S as a sum of differentiable functions. So essentially we just have, so each of these alpha sub n is just a constant, and this n power minus s, this is an analytic function. In fact, this is just analytic in terms of s, since as we know, n to the power of minus s, this is just exp, which is an entire function, of the natural log of n, which is a constant, times s, which is also a linear function, so it's analytic entire. So just to note that. So this is just a finite sum of differentiable functions. So we have, so make use of 6.4. Yes. Okay, so we have our domain S. S is open, so it is a proper domain. For each n, we'll define these functions, which are differentiable in S as a finite sum of differentiable functions. And then we'll say let K be subset to S, be any compact subset. And then we need to attempt to prove, yeah, we'll figure that out. Okay, so any compact subset, and then we can say, then we can find, oh, how do we want to do this exactly? So we're going to need to bound all of these terms somehow. I think what we'll do, so let me just do a thing here real quick before we lay out all the premises, because I don't know what they need to be. So when we do the sum, so we want to prove uniform convergence over a compact set K. So we'll do f sub n of s. If we do a of f sub n of s, then this will be the summation n equals 1 to capital N of oh, it should be actually not f as n. It should be f of s minus f sub n, as being the summation from n plus 1 to infinity of, then we have alpha sub n power minus s and then this will be bounded. We'll have this sum n equals n plus 1 to infinity. I hate it when it does that. Okay. We'll have a of alpha sub n, and then we'll have, okay, so here's the problem. We'll have a of n power minus s. We're going to need to figure that one out. So how can we bound n power minus s? So I think we're going to need to do a similar technique as what we did actually up here. We're going to need to do a similar technique as to this in order to show compact convergence. So when we have a of n power minus s, essentially we want to repeat some of these steps. So if we trace this whole theorem here, so we decompose s. We have a e to the sr is this, and then we have this is bounded by this. And actually, I think that's maybe enough. Actually, we don't even need n, do we? Or we don't need r, we just do... We can just do this part without the ceiling. A of e power s0 times n would be bounded by e of a s0 power n. That's actually, we don't even need to do that. Actually, yes, we do. This is useful. Okay, this is useful. This would let us do a of s0 with n. Okay. So I think we would need to do n power minus s. So just to be clear, n power minus s is equal to e to the power of ln of n times, whoopsies, ln of n times s, which is e to the power of, so we have ln of n times p1 of s multiplied by e to the power of ln of n times s0, and we're doing the absolute value of this, so this would be a n power minus s. It's bounded by, we have e power ln n times the real part of p1 of s, and then we'd also have times e to the power of ln n. Yeah, because we don't need to do right here. We don't need to do the ceiling of r. We can just do whatever it is, actually. Okay, so that'd be ln of n times a of s0. And I think that's essentially what we need. let me look at how that comes out. So we're going to do something like this. So let's see. Product of S bounded by this and that. S is, let me think on that. S is compact. Maybe we don't need to do that. Yeah, I think we need to use that. I think we're just going to need to do it all out. That's fine. Okay, so K be any compact subset, then we can find A in A sub re such that, actually, no, okay, so we can find A in A sub re such that, and then we need such that A of S is bounded by A for all S in capital K, the compact set. Since K is closed, actually we can say since K subset equal to S is closed, and we should have, or rather, it is possible to take A such that P1 of A is strictly greater than, what is it, 1 plus theta of alpha. So that's what we need. Yes, so since K is closed, it's possible to take this coefficient, this bounding number A, such that P1 of A is strictly greater than 1 plus theta alpha. So the reason that's true is S is such that all the things in there have the real part of P1 of S is greater than 1 plus theta alpha. Actually, that's not what we need. Okay, let's do it this way. Because that's actually not what we want. So the trouble here is we need to separate the first index from, oh, I know what you need to do. The continuous image of a compact subset is compact. So actually what we need to do is we can say if K is compact, then the image of exp of K is also compact, or we could do exp of negative K, capital K is also compact. We can find a to negative K, what do we want? exp of K is compact. We want to find, I think, a lower bound, and then we can just verify that we should have P1 of this image being bounded by something that we needed to be bounded by. Okay, let's try that. Okay. Okay, so for each n we have these functions which are differentiable. Okay, so let K be compact, any compact subset of S. Then since exp is continuous, also the image exp of S, or we can do exp of negative S, negative K, is compact. So there is sum bound A and so A sub re, that's already is A bound, so that we have e power minus s is bounded by A for all s in k. Okay, that's what we want. And I think from this, let me think this through. I think what we get from this is that e to the power of minus s, if we have this, e to the power of, or rather, n to the power of negative s is e to the power of minus s times log of n, which is also equal to maybe we do have to do this out. I'm trying to avoid doing it out, but this is definitely what we need to do. So look at this. So essentially we want to bound these exponentials, and I think we just want to, if we just do this all out, as we had done before, right up here. So this would be e to the power of, so we do get minus s, and then we also get power ln of n. I don't know if we want to do that. Let me think on that. Actually, if we work this out, so this works out to this sum k equals 1 to infinity, and we get, just like this, we get something over k factorial, we get minus s log n, or we do e to the s and then to the power of log n, e to the minus s to the power of log n. And we could instead write this using binomial coefficients. Yeah. So this would also be, instead, we could do log n choose. Oh, but we're not going to know if these are all positive or not. Okay. Okay, let's do it this way. K is a convex subset of S. Then we can find A such that we can say A, P1 of A is 0, and S, or rather, A of S minus P1 of S. gosh. These don't want to cooperate. Okay. Is bounded by A. Okay. Let's try that. So we just want, essentially, we just want to separate the first projection from everything else. Okay, so we'll find A such that P1 of A is 0 and S minus P1 of S is bounded by A for all S and K. Yeah, what's zombie? What? Okay. Okay, like A be a convex subset S, then it is bounded. So we can let theta be the infimum of real part P1 of K. And since K is closed, then theta of alpha plus 1 is strictly less than theta. Okay. We can also find A and A re such that P1 of A, or rather we can say as being specifically A is the supremum of the set of S in K, or rather S minus P1 of S such that S is in K. Although we don't want to do this either, we want to do A of S minus S, P1 of S, such that S is in K. So then P1 of A is 0 and A P1 of S, yes, or less than K. Okay. This is good. Now we just have to prove convergence. So we'll have now for each n in natural, we have n power minus s. This is just e to the power of minus s log of n, which is e to the power of, so actually this will be, instead of n power negative s into the exponent, we'll do n power negative s minus p1 of s, and then plus p1 of s. No, minus p1 of s again. So this will be n to the power of negative p1 of s times n to the power of negative s minus p1 of s. Or we could do it this way. P1 of s minus s, so we don't have so many parentheses and double negatives. So we'll just have this n power negative P1 of S out in the front. Actually, this should be not just P1 of S. We want to separate the real part of P1. We actually don't care about the imaginary part. So we can find theta and from the real part P1. Theta alpha plus 1 is less than theta. We can also find A equals the supremum of the A of S minus, and again, this is the real part of P1 of S. So then P1 of, the real part of P1 of A is 0, and A of S minus the real part of P1 of S is bounded by A for not less than K. Okay, now for each n we have this. So this is n power negative s, so we separate out the first index. That's fine. So we want to separate out the first index, and then this will be actually no, this is fine actually. We really don't need to do the real part here actually, because I think it works out in the end. So this just ends up being, so we have the real power, so n power negative P1 of S, that's fine. And then we just want to separate out this. So this will be, instead of just doing this, so let's separate out this part. And then over here, do this as the exp log of n times P1 of S minus S. Let me see how that looks. Okay, so n power minus P1 of S times, okay, so we have the summation m equals 0 to infinity of a fraction divided by n factorial, and that thing is the natural log of n times P1 of S minus S all to the power of m. Okay, this is definitely going to work. Okay. So n power S, negative S is this, is that. And then this gives us that A of n power minus S is preceding or equal to, so we have, actually, yeah, we just have equal to, no, yeah, we'll do preceding or equal to. So we'll have n to the power of the negative real part of P1 of S times the summation m equals 0 to infinity. Again, we have this fraction over m factorial and something to the power of m. But in here, we have log of n times a of P1 of S minus S. Yes, so this one here comes from this, and then this comes from this, and then this can just be bounded with, so we have the same thing, but we're just going to bound the A P1 of S minus S. This whole thing will just be bounded by just A. And then this becomes n power negative P1 of S, sorry, negative real part of P1 of S times, this will be e to the power of, we have natural log of n times a, which is again n to the power of a minus the real part of P1 of S. Actually, we don't really want to combine these, do we? so maybe cut down on a couple lines. Okay, I think this checks out. Okay, yeah. Let's put this in an alignment environment. Oops. Okay. Gonna erase these now. And let's actually put these here. Okay, so S is the set. Bound K, okay, and then we get, by combining, or rather we can say, now if we can bound the difference for each n in natural, we can bound the difference f sub n of s minus f of s over s in k as follows. So the way that works out is we have f sub n s minus f s. This is just the summation. We have n equals capital N plus 1 to infinity. And we have n power minus s, and this is alpha sub n times n power negative s. We want to take the absolute value of these, a alpha n, a n power negative s, but we know that this is just bounded by, we have our n power negative s is bounded by right here, this whole expression. Actually, we can go a step further here. Up on this previous line. So a power negative s, we can do, so this will be, yeah, let's just be a little more explicit here. We'll just combine these two lines and just be clear. So this is equal to a of these, which is bounded by, so we have this, and then the summation that does not fit into one line. Let's also do, let's do equality first. This is equal to this, which is equal to, we need to reapart, and then we have a lift parentheses, and here we have not that. Our parentheses. For sure that's going to roll over. Okay. Right, okay. Now we can do bound. So here, instead of doing n power minus real part p1 of s, we can just do n power minus theta. and then this has the A pull in, which is then bounded by that. This is still negative theta. Actually, yeah, that's fine. Okay, so we get per minus theta, and we still want here, this should still be theta. And then right here, this is still theta. I hope this is going to be enough. Oh, I forgot to do the slash. I forgot to do the slash twice. Okay. Now for each n natural, we can bound the difference over S and K as follows. So we get A, F, n, blah, 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 bounded by the summation, bounded by, and then this is, instead of n power minus S, we get n to the power of A minus theta. And I think that's it. Just about. So we can say yeah, that's it. Okay, so well, from convergence, so we could say since we have theta of A minus theta, actually we should do theta minus A, or rather, oh yeah, actually this is fine. So since we have the real part of P1 of A minus theta as being equal to, or sorry, this should be theta minus A, as being equal to theta, which is strictly less than, or sorry, strictly greater than 1 plus capital theta of alpha, it follows that the above summation converges for absolutely for any n. Moreover, it tends to 0 as capital N goes to infinity, giving, rather we can say, since this bound is independent of S in the set K and tends to 0 as n goes to infinity, this gives uniform convergence over the set. Uniform convergence F sub n going to F over the set K, which is compact convergence over S. So it follows from this theorem, compact convergence gives us differentiability. F is differentiable, so d alpha S is differentiable. Let's also be a little less redundant with our f of s function. Okay, so we have okay, for each n, we have this. and then that. And here we want to say we combine this difference fns minus d alpha s over s and k. So then this will be that. Since we have this, follows that the above summation converges for any n. Since this bound is independent of s and k and tends to 0, actually we don't really need absolute convergence, but since that's implied, since all the terms are positive, summation converges for any n. Since this bound is independent of s and k, it tends to 0 and goes to infinity. This gives convergence. This gives uniform convergence fn of s going to d alpha s over the set s and k, which is compact convergence over s. Perfect. Great. So that's nice. Yes. So we do have differentiability. Okay. What do we need next? Let me check my notes. So I think we have a few things. I want to prove, I think we need to prove that D is oh, I remember. Okay. Yeah, we need to prove that it's, well, we need to do something a little complicated. So let me think about how we want to set this next part up. Okay, so okay. Okay, so since our functions, actually we can say okay, we're gonna define a set, which is where these Dirichlet series actually converge. So we'll say so most of our theorems would be vacuous in the case that we have a theta value of infinity. That doesn't really do anything for us. So we will be considering the subset of a for which subset for which oh, this is interesting. Okay, let me think on this. This is interesting. We have a little bit of a recursion problem here. Okay, I'm going to do this. Yeah, so the fact that we've made these a little more general actually gives us a really weird problem. Okay, so here's the problem. I'll just show it to you. So we want to prove a theorem, which is that if we have d alpha s times d beta s, where alpha and beta both have finite theta values, then this is going to be d of alpha beta s, actually alpha star beta s. Here's where this is kind of tricky. What we actually want to mean here, what we actually want to say is that alpha star beta is such that if we index it by n, then this is the Dirichlet convolution, which is sum ab equals n of alpha sub n times beta, alpha sub a times beta sub b. This is what we want to do. The problem is that we already have alpha for every a and b, alpha sub a and beta sub b are elements in alpha and beta are in a to the n. So this is the recursion problem, or rather the sort of inception problem. The alpha sub a and beta sub b are in A, which means that technically this product here is already a convolution. I'm trying to not do this in such a way that it makes this dumb. I guess that's what I'm dealing with. I didn't have this problem. Yes, I didn't have this problem in the original draft. Yeah, so essentially the problem is, in the past we've been using, so we already have alpha A and beta B are in A, which is c to the n. We already have this this property. So I don't know. I have no idea. I think this is not, it's not useful to go into like a full recursion like this for a really particular reason. I think this is really hard to wrap my entire head around. This is just a bad idea. That's what I'm trying to say. Is this is a bad idea. I shouldn't do this. It will make this really confusing. I didn't have this problem in the original draft because all of the results were weaker. I didn't in the original draft I didn't allow alpha to be an arbitrary sequence in A. It was just an arbitrary sequence in C, which was then considered as an element of A using sort of the canonical bijection from C n to A. So I guess I'm just I guess I should just not do this thing that I'm about to do. I'm just going to restrict our sequences to just be in A, or rather in C to the N. I'm just going to do that. So okay, so hereafter we will consider, can you use the weaker results and then strengthen them later? I think the answer is yes. The answer is maybe, actually. So sort of yes and no. On one hand, perhaps there is, so what's interesting is if we define, I don't know, A prime as being equal to A to the N, and we define, if we define a star operation using this notation, and we define, so for example, we could say alpha c dot beta, for alpha beta in, this is a tangent, all of this is going to get deleted. For alpha beta in A prime, define, so we could define alpha c dot beta as being such that if we index this on some n, this is just equal to alpha sub n star beta sub n, which is the Dirichlet convolution. So it's pointwise Dirichlet convolution. But we could also have alpha star beta be this definition that we had up here, which was this one. So if we're just purely hypothetical, not actually going to use these definitions, but for an example, we could define these functions like this. The functions that we've been using in the past have been alpha dot beta, this pointwise convolution. So instead of doing A prime, instead of doing A power n, sorry, maybe A prime is equal to A to the n. So it's sort of the next iterative layer up. Do I use a macro to type alpha and beta? No. I use autocomplete. So I just AL and then I press tab and it autocompletes. Same thing with beta. BET tab. Although I guess this one doesn't really need the tab. You can also do, you can do the same thing with lots of things. I do the same thing with MathBB, which is this type of font. I also do, I can do this for math calligraphy. I just do MACA and it autocompletes to MathCal. And also MAFA and it autocompletes to MathFrac, which is a really weird font. Anyway, so where were we? So yes, so purely hypothetically, we could define this A prime as sort of this inductive layer above A, where in the same way that A is an extension of C, where we have infinitely many indices and the projections are complex numbers, A prime is an extension of A, where we have infinitely many indices and all the projections are elements in A. And then we could define, in the past we've been using this dot, which is just pointwise Dirichlet product. But we could also define this convolution, which in the context of Dirichlet series is what would happen. Yeah, so in the context of Dirichlet series, this is what would happen. And we would get this summation definition. As it turns out, if we do this, the triplet, so A prime with plus and this convolution operation, is an integral domain. Actually, we can say it's a topological integral domain. That means it's an integral domain, meaning it's just like our space in that it's almost like a field, except that, oopsies, it's almost like a field, except that we don't necessarily always have division defined. So it's almost like a field. It's an integral domain. It's also topological in the sense that all the operations are continuous and agree with the topology. Actually, as it happens, this integral domain is isomorphic to A with its own operation of plus and star, oops, which is quite startling, to be honest. They actually end up being isomorphic, so you gain literally no information by doing this, or no complexity. You just have to apply the correct isomorphisms to go between the two. It just turns out that way, which is interesting. Not what maybe you would expect. But yeah, it turns out that they're isomorphic. And if you're curious about what the isomorphism is, what you do is you define a bijection. Actually, we'll say, let me think on this. Let p sub 1, p sub 2, and so on be the prime integers. Then let var phi map n squared to n be any bijection. So this is a bijection. Then we can define for each pair of ij in n, define var phi, or sorry, not var phi, define other phi of e sub, oh gosh, let's do it this way. Let b sub n be in a prime be such that this is really complicated. Essentially what happens is, I'm just going to cut to the chase because it's really hard to articulate this. Essentially what happens is this set A can be generated by, A is just the generated by, we have C, and then we include the prime basis vectors E2, E3, E5, E7, and so on. Under, actually that's pretty much it. With the rules that E of I times J, EI times EJ is equal to EIJ. So this is sort of the rules to generate. If you have A and you want to generate from C, you just include infinitely many elements, contemplate infinitely many elements, indexed by the prime numbers, with this law that if you multiply two of them, then you get this thing. A prime is essentially the same thing. You can say A prime as being A, but you include, instead of E, we'll do F, F2, F3, F, it doesn't like this for some reason. There we go. F5, and so on. So all the prime numbers. Again, with the law that Fi times Fj is Fij. So we do this same essential sort of thing. So it's the same generation scheme. You just include a whole bunch of elements that you didn't have before, and you just have this law where they multiply through this way. And to get the bijection, to define the bijection, you essentially define any bijection var phi such that this set of f sub prime p times e sub q, the set such that p and q are in, I'll just do math BVP for primes, this set goes bijectively to the set of E sub P, such that P is a prime number. Yes, so you would define a bijection for phi, which bijects this set over to this set. And then you can just extend this bijection, no matter what you choose for this bijection. There's a unique extension to extend var phi as a bijective mapping from A prime to A, which is both linear and multiplicative and continuous. Phi sub underscore. Oh yeah. Yes. Yeah. Yeah. Yeah, so you're just generating a bijection. So both of these sets are countably infinite. And var phi just ends up with a unique extension to a continuous linear multiplicative bijection, which is, it's both an isomorphism and a homeomorphism. It's really weird how this ends up, but it just turns out this way. Essentially, when you do this, you can just consider these as being new prime basis vectors. So instead of having, like up here, instead of just generating C with just these ones, you could generate C with all of these ones as well as all of these ones in both. But then you could also just combine these two, and you just end up with more primes, basically. And you still have countably many prime basis vectors, and it just sort of works out in the end. You could alternatively, you could repeat this scheme, really, if you have any set. So here the indices for these basis vectors are natural numbers. If you take any integral domain, or rather, sorry, not any integral domain, any multiplicative group, no, it doesn't need to be a group, any monoid, so has an identity and has multiplication. So essentially a semigroup with, so you just have multiplication, it's associative, you have an identity, and you can just generate this ring with however many of these basis vectors, essentially. And that's kind of what it does. It's really strange, and it ends up being the case that it doesn't matter how many, it doesn't matter what your exact underlying like scheme is. If you have a unique factorization domain as the index scheme, it just ends up as the case that that you just get only the cardinality matters, only like the absolute number of indices that you're including matter. And here we're just have countably many indices stacked on top of each other. It's really weird, but how does it diminish the basis set? So technically it doesn't. So what we're doing is, because C is not just it's not just a group, it's not just an additive group, it's a ring. So in fact, by including all of these, we get all of these and anything that can be generated by finite sums and products. Technically, actually, this isn't enough to specify A. It's actually not equal to this. This only gives us elements which have finitely many non-zero entries. So for example, because we have E2 here, E2 times E2 is E4. So if we just had C with E2, then that would also give us E4, and so on. If you want to think about it that way. That we just have these as generators. But technically this isn't enough. Actually we need this, but then also closed under, infinite summations or something. This is sort of an informal way of thinking about it. But yeah, anyway, yeah, so I think I don't want to do this specifically because, so first of all, if we really wanted to get into it, we could formalize how this bijection works. It's marginally interesting. I think it's a little too complicated and useless to put in the paper. It's marginally interesting. Maybe someday, if we're interested, some other day we'll do it. But I think because of this, so they are isomorphic, so we don't really gain anything by doing this. So because of that reason, I think we're going to restrict. So in the past, we've been doing our coefficient sequences are in A. I think we're going to restrict our coefficient sequences to be just B and C. So let me get rid of these. So hereafter we consider only coefficient sequences alpha in C to the n, which is identified with A. Specific under the identification. We're actually going to do, okay, let's do this. Which we can identify with A using the canonical bijection iota, which maps A to, actually we'll just do C to the n to A. No, let's go the other way. Yeah, so we're just going to use this inclusion map. The inclusion map essentially just applies an isomorphism. So we know that our set A is the same as C to the n, formally speaking. So this iota mapping is just kind of, it's so that if we want to consider these as being different objects in a formal context, that we can. It's just to sort of separate the notation a little bit. So we're going to pretend as though A is not literally the same as C power n. But we're just gonna have this iota, this inclusion mapping, to treat them as if they are whenever we need to, and to not treat them as if they are whenever we need to not. Okay, so so we'll define A sum theta is defined as equaling the set of alpha in A such that theta of alpha is less than infinity, so it's finite. Actually, we can just do theta of eta alpha. There's no reason to not do that. Yeah, okay, we'll do that. Okay, so for the rest of our section, I think we're going to be focusing on this set A sub theta. So this set is essentially it's the set of singletons alpha in A, which again can be thought of as complex sequences, such that the theta value of iota alpha is finite. So previously we were considering our theta function compares, let's go back to definition, right here. So our theta function is attempting to compare alpha to essentially a polynomial, right down here, that specifies that. Essentially comparing alpha to a polynomial by taking its projection on each index and figuring out how does this sequence grow on each projection. If we restrict all the alpha n to be just complex numbers, then essentially you're just figuring out how does this sequence of complex numbers grow when compared to a polynomial, which is just really straightforward, you know, real or complex analysis stuff. So that's essentially what we're doing, and the only sort of special indication that we're doing here is that we're identifying, in order to take the theta value, we're identifying the set A with c power n. That's essentially what we're doing. So, okay, so let me actually make another specification. Actually, yeah, this is fine. Maybe this doesn't even need to be said. Okay, yes. Okay. So we'll do something else also. So we have this set that we're going to be considering, and we'll also notice, so since the Dirichlet series generated from D are analytic, or rather, since for any alpha in A sub theta, we have the Dirichlet series D alpha S being analytic in some right half plane. Our functions, our Dirichlet series, our functions, yeah. Functions are subject to identity theorem. And by grouping functions according to their agreement in some right half plane, we can prove that D is an isomorphism. Okay, so we want to make this a little rigorous. So essentially what we're trying to do is we're going to show that D is an isomorphism using in the context of identity theorem. So we're going to show that if we multiply two Dirichlet series, it's the same as convoluting their coefficients, or if we add two Dirichlet series, it'll be the same as adding their coefficients. So we want to be more specific about that. So more explicitly, for any alpha in A sub theta, we define D of alpha as an equivalence class. Functions analytic, which are analytic in some right half domain, analytic in some right half domain, and agree with D alpha S. We define D alpha as an equivalence class of functions which agree with D alpha S in some right half domain. Okay, so we'll do this definition. So D of alpha, this is defined as equaling the set of F which map some domain S to A, such that for all S in A, such that there exists theta in real, such that actually we'll do theta greater than theta alpha plus 1, such that for all S in A having real part of P1 of S greater than theta, S is in S, and F of S is D alpha S. Wow, that is really gross. Okay, let's break that up. Yeah, that's terrible. I hate that. Okay, so we want to say we'll say okay, we define equivalence relation. Okay. Okay, so more explicitly, partial function f mapping S to A, rather than just say A to A, is a function f mapping S to A such that S is subset to A. We define an equivalence relation over relation over partial functions such that for any S1, S2 subset to A, we assert. Okay, so we'll have let's see. Okay. Let me see how that looks. Okay, wow. Theta greater than theta alpha. Nope. Theta in real such that you can say holy crap. I don't even know what I'm trying to say. This is really... okay, we define an equivalence relation exists theta such that for all S in A, S is in S1, cap S2, and this is that. Okay. Let's do it this way. F okay. Yeah, that's what I'm trying to do. Okay, so here's what we're going to be doing. So first we're going to specify by what we mean by a right half plane. So we define a right half plane like this, so, or a right half domain as this. So A superscript real part P1 greater than theta. So theta is a real number. And this is defined as the set of S and A such that the real part of P1 of S is greater than theta. Pretty straightforward. And then we define an equivalence relation over partial functions. Such that for any S1, S2 subset to A and F mapping S1 to A and G mapping S2 to A, we have, so F relates to G is equivalent to there exists a theta in real such that we can say S1 cap S2 is a superset of A, real part P1 greater than theta, and F restricted to, shouldn't be subscript, this domain is G restricted to this domain. Nope. So right half domain is defined like this. So it's just where the real part of P1 of S is greater than some theta. And we're defining this equivalence relation over functions, over partial functions. So that for any sets S1 and S2 and functions F mapping S1 to A and G mapping S2 to A, we have the relation so we have this relation as there exists some theta such that both of their domains are both of their domains are supersets of this right half domain, and over this right half domain F is equal to G. And then finally, we just define D of alpha as the equivalence class of D alpha as the equivalence class of the function D alpha S. F maps A as subset A, and F relates to D alpha S. So it's an equivalence class of functions which agree on some right half domain. That's essentially all it is. Okay, so this is what we want to talk about. So this is what D of alpha is. It's the equivalence class of functions agreeing on right half domains. Okay, so we have F and G when they agree on Okay, we want to add some specifications. So, this relation is an equivalence relation. So this relation is an equivalential relation, which lets us define d alpha as the equivalence class of the function d alpha s. Okay. So this is what d of alpha is. We also define this class, math tau d, as being the image of d a sub theta. Okay, so, for any two f sim g, or rather, we can say, for any two classes, we can say x in xy in this class D. So to be clear, in case we're confused, so right half domain is where real part P1S is greater than theta. This relation is satisfied when two functions agree on one of these right half domains, which is just this whole mess. And D of alpha is the equivalence class of D of alpha S. So D of alpha is just the equivalence class for D alpha S for agreement on some right half domain. Just to be super clear about that. So we can actually define, also this script D is just the image of this Dirichlet D alpha. So it's just the script D is the set of all these equivalence classes of these. Okay, so for any two classes x, y in script D, we can define the sum and product as follows. So we have x plus y is defined as the set of f plus g such that f is in x. Actually, we can say the set of h, which maps S to A, such that S is a subset to A, and H relates to F plus G, such that F is in X and G is in Y. And likewise, we'll do this for the product. H, which relates to, or rather we can say instead of H, H, which is related to F plus G, such that this works a little better. That's actually a lot better. Okay, So we're defining sum and product over elements of D. We're defining sum and product this way. So it's another equivalence class. So it's just the equivalence class of H, functions H, such that in the addition case, H is in the class for F plus G, where F is in the class X and G is in the class Y. And likewise, the product X times Y is the class of all H, such that H is relating to any F times G, where F is in X and G is in Y. We can also do, yeah, actually that's fine. So this is an equivalence class. We're not going to go through the proof, but essentially we can show that in fact, if we pick any F and G, in X and Y respectively, and then we pick any second function F2 and G2 in X and Y, the sum of F plus G will be in the same equivalence class as F2 plus G2, and likewise for the product. So actually, really, it's fine to just have this. So these are sort of unique equivalence classes. They will all agree. So these are fine. And so what we want to prove is that, first of all, we want to prove that our script D function, or our set, our class of equivalence classes of functions, we want to prove that this is closed under addition and multiplication. And we also want to prove that in fact it's an isomorphism to a theta, or sorry, it's isomorphic to a theta using the function D. So we have these definitions for the script D function. So D is essentially, we can think of this as the set of all convergent Dirichlet series, up to, identity on a right half plane. As we can think of it like that. Okay, so I guess we'll just start right off with our theorem. So our theorem is for any, we can say alpha, beta in A sub theta, we have D of alpha times D of beta as equaling D of alpha times beta. Okay, so this is one. We're going to put this one on hold for a second and prove the easier one, which is just for summation. So same thing, but with sum. So for any alpha, beta, and A theta, we have D alpha plus D beta is D alpha plus beta. So that's what we want to prove. So the sum will be a lot easier than the product case. Significantly easier, in fact. So for the sum case, we'll just say, so we'll say let f be in D alpha and G be in D beta, then it is enough to show that f plus G is in D alpha plus beta. So we're just going to prove that it's in this equivalence class, and then because f plus G, or rather because D alpha and D beta is the equivalence class generated by f plus G, then if f plus G is in D alpha plus beta, equivalence classes are disjoint, so if there's any intersection, they have to be identical. So we'll just take these functions. So we'll say, actually, more specifically, we can say let f be in this and G be in this. Actually, we can just say let f of s be equal to D alpha s, which is in D alpha, and G of s equaling to the function D alpha sorry, d beta of s, which is in d beta, then it's enough to show that the sum is this. So take any s in, or rather take any, yeah, s in a such that, actually we can do it easier, s in c, such that the real part of s is greater than theta of alpha and theta of beta. Okay, so we'll do that. Actually, maybe we maybe do a lemma. No, actually we don't. This is fine. Take any alpha in this such that s is greater than, yes, okay. Then we have, f of s plus g of s. This is equal to the sum, n equals 1 to infinity. We have alpha sub n times n power minus s. And we're adding this summation, n equals 1 to infinity, beta sub n, n power minus s. But this is just this summation, n equals 1 to infinity of alpha sub n plus beta sub n times n power minus s, which is just the alpha plus beta with s. Okay, we are actually going to need a lemma for the product one. Yeah, in some cases it's really easy, but just let fs be this, which is in that, and g of s be that, which is that. So that f plus g is in this. Take any s in a such that of s beta. Yes, so that's pretty easy. Okay, so that's that. So for our lemma, for our product case, we want to say, let alpha and beta be in a sub theta. Then the convolution alpha star beta is also in a sub theta. Actually, we're going to do something a little better. We're going to say the theta value of alpha plus alpha times beta is less than or equal to the theta value of alpha let me think on that. Less than or equal to the theta value of alpha, I think, plus theta beta. Which is also less than infinity. So this is a little different from the one that you had previously, and actually maybe we would do want to use our inclusion operator to make this clear. So previously we had where is it? This, which looks almost the same, but this is actually not what we're trying to prove. So right here, we have, these are sequences in A, and their product is pointwise product. But down here, we have sequences in C, which are identifying with A theta, and we're doing the Dirichlet product, which is different. So maybe we want to be a little more explicit with the fact that these are different. So I think we're going to do that. Yeah, so I'm going to make sure, I'm going to bring this inclusion operator back. Okay. 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 That seems a little better. Okay, so theta, so this is still valid. So let f do this. We'll do iota here and there. Okay, so what we're doing with this inclusion mapping is that, so we are sort of differentiating, not differentiation, we're making separate the A and Cn sets. Formally they're identical, and this iota is just the expected bijection between them, which under our current formalization is technically an identity, but we're going to pretend like that's not true. We've specified this set, so we're going to use this iota whenever we need to. So we've specified this set, A sub theta is the set of alpha in A such that when considered as a complex sequence using iota has a finite theta value. Once we've set up this set, what we also want to do is to group together Dirichlet series or functions by their agreement on some right half domain. So to do that, so we define all these equivalence relations, and we let d of alpha, so again alpha is just in a theta, let's specify that. So finally, for alpha in a theta, so we define d of alpha as the equivalence class of this function. We define this as the equivalence class of the function d of the inclusion of alpha, so iota alpha, which is alpha when considered as a complex sequence using the variable s. So that's just this. So d of alpha, alpha is an object in a theta, it's a number in a theta. And d of alpha is the equivalence class of all these functions, these Dirichlet series. So d of alpha can sort of be considered a generating function, except that it produces equivalence classes of functions. That's fine. We're just going to, I guess, have this there. So d of alpha is sort of like our generating function. It takes alpha and it gives us a function, and it sort of agrees with the Dirichlet series. So we also have this image script. D is the set of these images. We define the sum and the product. So our proofs are to show that. So these are well-defined equivalence classes. We're just going to acknowledge that and not prove it. But what we are going to prove is that the sum and product, so that this script D is closed under sum and product. So the sum case is sort of straightforward. So we have d iota alpha with s as a function, and d iota beta with s is in d beta. So it's enough to show that the sum d iota alpha with s plus d iota beta with s is in this d alpha plus beta. And that's the easy part. Okay, so to do this product part, so what we want, so this should be iota alpha times beta inside. Iota alpha, iota beta. Okay, so now we've thoroughly differentiated this, made it different from, distinguished this from the previous theorem. So previously we had, if we multiply two sequences pointwise, then we have this inequality. It turns out if we convolute them, we also have this inequality. Actually, this should not be, we don't even need this less than infinity here. I think it should just be like this. Okay, so essentially the way that we'll do this is we'll say let theta 1 be greater than theta of iota alpha, and theta 2 be greater than theta of iota beta. Then by the third characterization, we can find A, B, and A re such that we have P sub n of beta. Actually, we want to say the absolute value of P sub n of beta is less than or equal to, actually these don't even need to be in A re, they can just be in A. This is less than or equal to, so we have A times n power theta 1 if this is alpha. And the same thing so we'll do, yeah. And beta being bounded by Bn theta 2. Right, so theta 1 greater than capital theta of alpha, theta 2 greater than capital theta of beta. Then we find these bounds. So in this case, we can take A, B, and C. Actually, don't even need to be in the complex numbers. We can actually just say these are A, B greater than 0. Although I think we maybe don't need this. Yeah. No, we do. So we find A, B greater than 0 such that for all n, absolute value Pn alpha is less than or equal to this, and Pn beta less than or equal to that. Okay, so we then have so if we do P sub n of alpha star beta, we do the absolute value of this. This is going to be less than or equal to the sum. We have AB equaling n, absolute value of PA of alpha times PB of beta by triangle inequality. Then this is bounded by, we still have the summation, sum AB equals n, but then for, oh, we don't want to do this, do we? Let's do IJ, JK equals n. Because we're already using A and B. This must then go to the sum, so we have PJ alpha is bounded by, so we have A times J power theta 1. And then for B, we have B times, sorry, for beta, we have B times K to the power of theta 2. Actually, let's do this easier. Let theta be greater than theta iota alpha and theta iota beta. So instead of having theta 1 and theta 2, we just have a single theta. And this will make it a little easier on us. Okay, but then this is just equal to, so we have sum jk equals n. We have a times b we can factor out. We have j to the theta and k to the theta. Let me render all this real quick. Okay, right down here. So you have j to the theta and k to the theta. J times k equals n. So this is just n to the power of theta. And here is maybe somewhere that we should have been thinking ahead. Oh, right, okay. So this is just abn power theta times the summation jk equals n times 1 of just 1, because n power theta is independent of j and k. Right. So this is where we're going to have to just sort of I think just sort of assert a thing as being true, because we don't want to have to prove it. So the thing that we're going to assert is, so we'll say okay, so the thing that we're essentially asserting is we're considering this constant. Hope you can see this well. So this constant, we're using this sort of fancy stylized 1. So this is just defined as the summation of all these e sub k's. So it's such that, yeah. So it's such that each projection is just 1. So this fancy stylized 1 is 1 on each projection. So the assertion that we need for this lemma, so this utilizes the fact that this 1 squared is in a sub theta. And we'll make a note, this is proven. And actually we can say theta 1 squared equals 0 is actually what we want. I'm going to say it's proven in Appendix D, and we're going to just add a to-do note. Also, I still have no idea what my appendices are doing. I have 4 appendices and like 3 theorems in them, so that's fine. Appendix D doesn't even exist yet. Okay, so we're just going to use this fact that if we have this 1, which is all these, just all 1s, that 1 squared, bold 1 squared has a theta value 0. And we're just going to assert this and prove it later. So this is proven in Appendix D. This is a well-known property, so I'm not worried about this. This is very well known, but we will put it in the appendix just for fun. Yeah. So anyway, so once we get to here, so this is AB n power theta. So down here, once we get to this, we can consider this as actually being. So this is AB n power theta, and then this is PJ 1 times PK 1, which is just AB n power theta times P sub n of 1 squared. Just like that. That's not going to fit. So this, let's go to that. Let's go to that, which is, we can all pull all of these out. So we can kill this line here. See how that looks. It's a little better. I think that's probably fine. We can always fix these later. Okay, so that's that. And then we can say, since we have theta of iota, oh yeah, this should be theta of iota, m1 squared. Forgot about the iotas. Okay, so, oh gosh. I think that's just a server error, not my code breaking. Okay, well that thinks. So this is 0, and for any epsilon greater than 0, you can find c greater than 0 such that the m1 squared, so this is p n squared is less than or equal to, this should be absolute value, less than or equal to c n power epsilon. So then we have this. This is less than or equal to a, b, c, n power theta plus epsilon. Right. So essentially, so we just take this projection of this convolution, expand the definition, apply triangle inequality, which I am gonna do out all the way. Let me put this in a line so that we can space this out all nice. This is this absolute value, these summations. Which is bounded, so we do triangle inequality, then we do bound alpha and beta, factor these things out, and then this is that. And then we are going to need to do that. And right around the time we do this equals sign. Actually, let's do one better. Okay, so yes, so we've bounded this convolution by a times b times n power theta times pn of 1 squared, of bold 1 square. So since theta iota of bold 1 square is 0, which we are apparently proving in our appendix, then for any epsilon greater than 0, so because its theta value is 0, epsilon is greater than its theta value, so we can find this constant c greater than 0 such that these projections are all less than or equal to c times n power epsilon. But then that means that this projection, which is this, is less than or equal to a, b, c times n power theta, and then this should be plus epsilon. Excuse me, I had to sneeze. Right, plus epsilon, and then since epsilon greater than 0 and theta greater than 0, sorry, greater than capital theta of these ones, since epsilon and theta are arbitrary except for epsilon greater than 0. Okay, so yeah, so by the third characterization, we thus have beta of iota alpha star beta is less than or equal to theta plus epsilon. By taking theta, or rather by taking epsilon to 0 and theta to oh, that's interesting. It's not the sum. I was wrong. It's actually the minimum. Or sorry, the maximum. This doesn't apply for the pointwise product, by the way. In general. Okay, so beta a star, a theta, then if we do this convolution, then it's less than or equal to the maximum. Okay, so theta greater than these, but theta characterization, we find blah blah and so on. Because the summations, that's that, and then since this is 0, we find this epsilon greater than 0, and C to bound this, so that this is less than or equal to that. Then by the third characterization, the theta value of alpha convolute beta, alpha star beta, is less than or equal to theta plus epsilon by taking epsilon to 0 and theta to its minimum, taking epsilon and theta to their lower bounds. We have the convolution. Right. So essentially we just show that, well, on each projection, this alpha star beta, which is just a single thing, can be bounded by some constant AB, ABC n power theta plus epsilon. And the only requirement was that epsilon was greater than 0 and theta was greater than this maximum. By taking epsilon to 0, we just get that the theta of alpha star beta is less than or equal to theta, and by taking the theta to its minimum, we also get that this is less than or equal to the maximum, which is the claim that we're asserting. Okay, so so that is that. So now the theorem becomes a lot easier once we have this. So the theorem is just that the d alpha times d beta is d alpha times beta. And the proof for this is, so we're going to, I think, so restrict S and C such that, I think this makes it easier for some reason, although I forget why. Actually, no, we don't really need that. Restrict S and A such that, so we have the real part of P1 of S as being strictly greater than the real part of P1, or sorry, strictly greater than the max, or rather, you just have both of these. which is right up here. This. Then we have, so this goes on similar to the summation. So we have, oh, that isn't even correct. That fixes that. Okay. So let's see, where were we? Okay, so restrict S such that this is greater than these. Then we have, so we have D of alpha S, and this should be iota alpha S. And we're multiplying D iota beta S. This doesn't make sense also. Let me fix that real quick. This should be p sub n of alpha. And this should be p sub n of beta. Okay, that's better. I also am going to sprawl this out a little bit, specifically because I don't want this to be cut off. So this, which is that, which is that, which is this. So what we can do is we can say, cut it off at this inequality there. Okay, this will be pj of this, pk of that, and that's that. Okay, that's a little better. Yeah, okay. Okay, so that's such as this. Okay, so we have this product. So this is equal to, so we're gonna do out the summations. So we'll do n equals 1 to infinity. We have n power minus s. And then we have p sub n of alpha. And we're actually multiplying this by the summation. We'll do m equals 1 to infinity of p sub m of beta times m power minus s. And actually we'll be a little more suggestive. We'll do j equals 1, p sub j, j power minus s. And we'll do k equals 1, p sub k, k power minus s. Okay. We can just rearrange these, so we can just use distributive law to pull this summation, and also continuity. Pull this summation out like this. And then we end up with, we're also going to take out this out there, and this over there. Okay. So by absolute convergence, it is justified to rearrange the above in the following way. So what we're going to do here is we're going to do a partition. Okay, so we have this whole thing. We end up at this sort of mess. What we're going to do is we have this double sum. We're going to partition this double sum. So since we have absolute convergence, we can rearrange these however we want. We're going to partition this double sum by doing a sum from n equals 1 to infinity. And we're going to do a sum across all jk where the product is equal to n. So ordered pairs j and k where the product equals n. We can just do that. We can just rearrange them like that. And this makes it really easy because now this is just a convolution. So we get our j and k to power negative s. They're being multiplied together. So this just becomes n power minus s on the front. Now let's just factor that out. And then this is now sum n equals 1 to infinity. And we have p sub n of alpha star beta. And this is now just d of iota alpha star beta with s. And that's it. We're done with that. And that's the proof for product. So that's nice. So yeah. So that's pretty good. Okay. So this does actually prove, this almost proves isomorphism. It actually proves homomorphism, which is nice. Actually what we want is isomorphism, which requires that it is a bijection. Since we defined this script D, this set, this by definition is just the image of A theta with D. So we already have that that's a surjection, so we actually just need to prove that it's an injection. So theorem for any alpha, beta, and A sub theta we have d alpha equals d beta implies alpha equals beta. So it's injective. Okay. Actually, we can be more explicit. The function d, the mapping A sub theta to script D is an isomorphism. Okay, so we already have that D is linear and multiplicative, so it is at least a homomorphism. Moreover, by definition, D is surjective. By definition of D equals the image D of A sub theta. So we need only prove that it is injective. Since D is linear, it is enough to prove that the image, or sorry, the set, or rather, it is enough to prove that d of z equals 0 implies z c equals 0. We want to be specific. This is 0 in as a function, the 0 function. Okay, so we're going to assume that d of alpha is the 0 function, and then we're going to prove that alpha is 0. So the way that we do that is by contradiction, suppose that alpha is not 0. Then let k be equal to, remember this function, z of alpha. So k is z of alpha. So then we have d of alpha, or rather we can say, so then all sufficiently alpha is not equal to 0. Further, we're going to let theta be greater than capital theta of iota alpha, so we can find a greater than 0 such that absolute value of p sub n of alpha is less than or equal to a times n power theta. For every n. Okay. Okay, so setting up all these premises, so by contradiction, suppose we have an alpha and a theta, which has the 0 function in its d alpha equivalence class, but alpha is non-zero. So we can let k be z of alpha, so again that's the lowest index for which alpha is not 0. So we let, okay, so let k be this, and find a theta greater than capital theta of iota alpha, such that, this and a greater than 0, such that p and alpha is less than or equal to a n power theta for every n. Okay, so now we have, so we'll do, we have, what am I going to do? D of alpha, comma, so this will be iota of alpha, comma s, for, let's say, r sufficiently large, we have for sufficiently large r greater than 0, we have 0 sub 0 function at r is equal to d iota alpha at r, which is equal to the summation. So we have n equals, initializing at k to infinity, we have p sub n at alpha times n power minus s. But we're actually going to rewrite this as p sub k of alpha times k power minus s plus this summation of n equals k plus 1 to infinity, and again we have p sub n alpha n power minus s. Okay, so what we can do is now, so we have 0 equaling this summation. So what we're going to do is we're going to divide by k power minus s, and we're going to subtract p sub k of alpha. So we have negative p sub k of alpha, so we're going to divide by k power minus s. So this is equal to the summation, we have k power minus s times the summation n equals k plus 1 to infinity of p sub n alpha times n power minus s. So we do have this, but also what we can do is we can take the absolute value of this and this negative will cancel. So absolute value of pk alpha is the absolute value of k power minus s times all this. And actually just what we need to show is just that this right side vanishes. So we're going to show that this right side is, we're going to show that it's 0. So this will be less than or equal to, right, we have absolute value pk, or sorry, k power minus, oh sorry, this shouldn't be s, this should be r. We're using a real number because it makes everything easy. R is here, and there. Still have k minus r, so this will be, and we can actually, because r is real, we can pull this out to the front. Pk minus r, absolute value, and so on and so forth. Okay, so this will be less than or equal to, so we still have k power minus r, then we have the summation, n equals k plus 1 to infinity of, so instead of doing p n alpha, we can bound this with a n power theta, and then we still have n power minus r. And then we just need to bound this summation. So we can also do this as theta minus r. Okay, so this will be, so we have a k power minus r, and then we have the summation. So this will be less than or equal to, so we are essentially using the integral test. Here, although we're being a little bit more specific than the integral test. So k plus 1 to infinity. And then this is n power r minus, sorry, theta minus r. Since r is sufficiently large, we can assume this converges. Let me put this all in this alignment here. Okay, so we have this, and now what we want to do is that this is less than or equal to, so we still have a times k to the power of minus r, and then we want to bound this. And so I think what we can do is to bound this, we can have the lowest term, n power theta minus r, where n is k plus 1, and then we can add the integral from k plus 1 to infinity of x power theta minus r dx. Oh gosh, I didn't do a new line. You thought I divided by k power minus r? Yes, you are right. Let me fix that. Yes, so we should have k power positive r. Yeah. So we do have, so here, and we divide by k power, yeah, so we should be multiplying by k power r. So these should be positive, positive, and positive here. I think that's correct. I think that's all of them. 2, 1, 2, 3, 4. Yes. Also, I didn't do a slash here. Okay, let me double check these. So we do have this. So we have subtract this off, divide, multiplied by k power r, takes the absolute value, summation. Okay, this checks out. And then we have absolute value. So this is less than or equal to this. So we just bound it by this. Pull out the a, and combine the exponents, and then bound this by, so we have a k power r times k plus 1 theta minus r. I think this is okay. Plus this integral. So this is sort of integral test. It's because for sufficiently large r, this is decreasing for so long as theta minus r. In fact, so long as the sum converges, then the integrand is strictly decreasing. It's the same logic as the integral test. But anyway, so we end up with a summation. So we can bound this by the integral of the function plus the first term, which is this, which we know in advance this is going to work out. So that this will all trend to 0 is essentially what we're gonna prove. So we have this, and then we just work out this integral. So we still have a k power r times, we still have k plus 1 power theta minus r, and then we have this integral. So we're going to work this integral out. And actually, I'm just going to make life really easy on myself. I'm just going to do it in this computer. Expression, so our integrand is x power theta minus r. That's disgusting. I hate that. That's better. That's what I would work out if I was going to do it. Yeah, that seems correct. Okay, so we're going to just plug that in. So this integral works out to we have k plus 1 to the power of theta minus r plus 1 divided by theta minus r plus 1, and then this should be negative, so it should actually be negative theta minus 1 and positive r. let me verify that this all makes sense. And then essentially we just do a limit as r to infinity, assuming that this all checks out. So we are going to get a factor of k plus 1 to the power of theta. That's just going to be sort of hanging out. That's fine. And that actually takes care of the thetas in the exponents. Okay, so I think this is fine. So we end up with, so we still have a, k power, instead of r, so we're actually going to do, we're going to distribute through this k power r. So actually let me just copy this whole thing and work on it like that, so I don't make any silly mistakes. So we're going to have, distribute this whole k power r in, so, oh right, because this is k plus 1. Is it possible for us to get around that? I think the answer is maybe no. Because we're supposed to be showing that this is 0. Hold on, let me think this out. Because this should be, this is the dominant term. The extra k plus 1. Yeah. The extra k plus 1 is just a constant. The leading term is effectively r to the power of, sorry, k plus 1 to the power of theta minus r plus 1 divided by r. This one and this one will cancel out to a constant. I hope I did this right. Let me check this real quick. This one. Let me actually show you. I'll show you what I'm doing. So I'm essentially just going to plug this into here. So we have this whole expression, which is this thing on the right, and we're going to add to this k plus 1 to the power of theta minus r, and then we're going to multiply this entire thing by some constant a times k to the power of r. And we want this to go to 0 when we limit r to infinity. Sure, that's positive. Yes, it's positive. That's positive. Theta's positive. Oh my gosh, it's 0. Okay. So it thinks it does work out to 0, which is good. So I feel confident. Okay, so we'll work the whole thing out explicitly though. So we put through the k power r to everything. Actually, let's not do that. We'll keep the k power r. Oh gosh, k power r on the outside, which actually, just to be safe, I'll do this. We'll keep the k power r there, but instead we're going to extract the k plus 1 power minus r. K plus 1 power minus r. K plus 1 power minus r. And while we're at it, we might as well extract the k plus 1 to the power of theta. So this will end up being power theta, that's 1. K plus 1 power theta, that's just power 1. The exponent goes away. And we end up with this. And we don't need the parentheses and the numerator there. Oopsies. Okay. K is constant, theta is constant, r is heading to infinity. And that's all we need to know. So, now we can just limit it to infinity. So, So because this is just set value, p sub k of alpha is just a constant. This is a limit, and r goes to infinity of this whole mess. So when we do this limit, this entire fraction, so k is a constant, so this whole fraction, this one, tends to 0, which means this entire factor tends to 1. So we can just ignore that. And then we have a times k plus 1 power of theta times this limit. R goes to infinity. We have k power r times k plus 1 power minus r, which equivalently is k over k plus 1 power r. Oops, power r. Okay, and that works out because this is less than 1 and greater than 0. And that's it. Let me double check this. So we start with this. So we have 0 is just the 0 function at r, which is, as apparently by premise, this 0 function is in d alpha. So 0 is the 0 function at r, which is just this d alpha at r, which is this summation by the Dirichlet series. We then pull out the lowest term, so because we have z of alpha is k, we pull out this lowest term. So we have this term plus this summation is 0, so we subtract off this term, multiply it by k power r, and take the absolute value. Apply triangle inequality, and we end up with this. And then we, since this is strictly decreasing for sufficiently large r, we can bound this with an integral, which is just the first term plus replacing the summation with an integral. And we just work out this integral like this. We factor out some terms, and then because this is constant with r and it's equal to this, then we can just take this limit as r goes to infinity. So this whole fraction goes to 1, and we factor out this a, k power r, and k plus 1 power theta, so we just get this limit of k power r, k plus 1 power minus r, which is this, and this is 0. And that is the whole proof. But this is a contradiction, as expected, so as expected, this is a contradiction of the fact that k, which we said was z of alpha, so we should have p sub k of alpha non-zero. From this contradiction, we conclude that such alpha does not exist. So D is injective, proving the theorem. So that's it. So our theorem is that it's an isomorphism. We already proved that it's linear. We already proved that it's multiplicative, so it's at least a homomorphism. And we already have, by definition of this set, we already have that it's surjective. And because it's a linear function, to prove that it's injective, it's enough to prove that it has a unique 0, so its kernel is singular. And that's what this whole proof is. So we just essentially we just show that if it's not 0, then it doesn't tend to 0 fast enough to be 0, and that's pretty much the whole proof. That all of the smaller terms, so after the biggest term, the smaller terms are just not big enough to sort of match it. And that's it. So yeah, so the function, so the Dirichlet series function, or rather, this function D, which we've defined as the equivalence class of convergent Dirichlet series on a right half domain. This function is an isomorphism between the set A sub theta, which is, I'm sorry, this should be capital theta. The set A sub theta, which are the values in A which will converge when put through D. It's an isomorphism between A sub theta and this class of convergent Dirichlet series D, which is pretty cool. It's pretty neat. So that's going to be really useful for us in the near future. Let's go, we can go for, I think, maybe another 30 minutes, and then I'll have to call it quits. But we can go for a little bit longer. Okay. So we have this. I think the next thing we need to do is, there's a proof about some continuity property of the D function. So the theorem is, we'll say let alpha be in A sub theta, and here we're going to have a sequence actually. So we'll say let alpha sub n indexed by n a natural be subset to A sub theta have a limit alpha sub n goes to alpha 0, which is in A sub theta. Actually, we can just say such that so alpha n goes to alpha 0, and be such that there is an upper bound, so just say A in A sub theta, such that A of alpha sub n is bounded by A for all n. Then d alpha, I guess we need a topology, don't we? If we want to do that. We'll just say d alpha s goes to, sorry, d alpha n s goes to d alpha s. We will have to give it a topology, I think. Okay, so what we want to say is if we have a sequence tending to a limit, and that sequence is bounded by some constant sequence, A, for all n, then what we want to say is that this d alpha n goes to d alpha. We don't have a topology for our script D class, so we're going to need to specify that in this proof, or before this proof. So we can say we can also give D a topology. Actually, I really don't want to do this. Let me just state the version that doesn't require me to do as much work. Okay, so let's say let alpha n be this and have a limit, alpha n goes to alpha 0, and with an upper bound a sub theta such that an is bounded by a for all n. Then there is theta yeah, okay. There's theta in real such that S in this half plane re P1 greater than theta have d iota alpha in S goes to d iota alpha 0 also with S. This proof theoretically should be really easy. It's basically just dominated convergence. I limit alpha n go to alpha 0, upper bound such that that's better. Okay, so so the theorem is if we have a sequence in a theta, and so to be clear, not a single object in a theta, but a sequence of objects in a theta, which tend to a limit, which is also should also be in a theta. Actually, I guess this is redundant. Yeah, and they also have all of these have this upper bound a in a theta for every n. Then there's some right half domain over which these series, the Dirichlet series, converge pointwise. So the proof should be straightforward. So we essentially just say this follows from dominated convergence. Convergence, so we'll just say let theta be equal to capital theta of a plus 1. Then we have d, or sorry, let's do this. For each n, we have d of iota alpha sub n with s. This is just the summation. N equals 1 to infinity. And we have p sub, oh, let's not do n again. Let's do k equals 1 to infinity. P sub k alpha sub n times k power minus s. Okay, and then we can say, notice that for each k, we have this whole expression goes limits to, or we should say for each fixed k, we have this limit to the same thing but alpha 0, as n goes to infinity. And moreover, we have this whole expression. This is the absolute value. Actually, yeah, we'll just do absolute value of this whole mess. Actually, oh gosh, because we're doing S, not necessarily on the complex plane. Okay, let's do it this way. We'll do this as a lemma, because I think we're not going to use it more than once. So I have alpha and blah blah, then there is this for which S, so instead of doing S in this right half domain, we'll do it in the right half complex plane. Okay, so this makes it a little easier, so we don't have to mess with the indices again, because this is fine. It's fine to only have this for the complex plane. Okay, so go to infinity, moreover we have pk alpha n. Pk alpha n times k, this is less than or equal to, so we have p sub k of a times k power negative theta, which is absolutely summable over k. So it follows from dominated convergence that the limit holds. Okay, and then we'll just say d iota alpha n s. So if we do this limit as n goes to infinity, this is equal to summation of this limit, but this is just d of iota alpha 0 with s. Okay, so the reason that we've done this as a lemma is because I think we're only going to use it once. Also, the reason that we've only done this for the complex plane is because the thing that we want to use it for, is going to follow from identity theorem. And actually, I think this is one of our last theorems, like at all. Sans like maybe some odds and ends. So that's actually kind of exciting. Okay, so we'll say let alpha be in a sub theta, alpha be in a sub theta, and f be complex analytic at p1 of alpha. Actually, we can just say at alpha. Then f d alpha equals df alpha. Yeah, so, yes. So if alpha is a sequence in A theta, and f is a complex analytic function, analytic at alpha, then we have this permutation. That if we have f of d of alpha, this is d of f of alpha. So again, this f of d of alpha, we haven't technically defined a composition, but we could just consider this f d alpha as, actually let's just specify it. So in the next theorem, a composition, rather, we define the evaluation f d alpha as follows. Actually, we can say we're going to be specific. We should maybe be doing this as not an evaluation. I think this should be technically be a composition. S arc d alpha. Okay, so I think that's fine, because in the sense that d alpha is an equivalence class of functions, this would just be pointwise composition. Okay, and that's a little better. So we're actually, I think we're not going to be able to prove this today, because we need a rather complicated result. We can probably get that result out of the way though today, but I think we might not be able to finish today. Actually, it's already 6:30. Which is when I said I was going to stop. Okay, let's just be specific about this, and then maybe we'll stop. So we'll say where f is some function, and alpha is in a sub theta. So where f is some function, a partial function. Partial function, we can say defined in a neighborhood of P1 alpha. Actually, we can just say complex analytic function. Okay, so alpha is an A theta, F is complex analytic. Actually, maybe I can't just define this as an evaluation. Okay, so what we're saying is, So now we're going to use this language. So this evaluation, if we have a function, a partial function, which is complex analytic, actually I think it doesn't need to be a complex analytic. If we have a partial function which is defined in a neighborhood of alpha, then we define the evaluation f of d alpha as the following equivalence class. And so this equivalence class is the set. So we'll say f of d of alpha is defined as equaling the set of H, such that H is relating to, under our equivalence relation, f of g of alpha, f of g of s. Actually, we can just do f of g, f compose g, such that g is in d of alpha. So it is essentially just the composition. I wonder if this is going to work, actually, for a particular reason. Okay, so the particular reason that I'm not sure about is that we've defined our equivalence classes as being defined in a right half domain instead of a right half plane. If it's on a right half plane of the complex plane, then in fact, if it's just a right half plane, then as the real part tends to infinity, a Dirichlet series tends to zero uniformly, regardless of how you approach it, regardless of how the real part approaches infinity. I don't know if that's true. I don't know if that's true for in this higher context. So I guess we can just figure it out. But nonetheless, we've definitely, I think we've definitely gone over time. And I need to stop for today. So we will. This is what we have to look forward to. This is the last sort of thing, sort of major theorem. Everything after this is just smaller things, less important, or just sort of novelties. There is something that we can set up here. So a result that we're going to need, yeah, very exciting. So a result that we're going to need for this is let me see if I can remember this. I think it's 1 over 2 minus PM bold 1. Will it keep going for a while? That depends, I think, on how much sort of extra stuff we're going to do. It could very easily be ended with this theorem. We could very easily end with this theorem, for sure. There would not really be any reason, I think. There would not be a super huge reason to keep going. We could, but we don't really need to. Yes, this is correct. Okay, so yeah, but before we go, just sort of get you thinking about it. We have this constant, so just to be super zoomed in, this kind of actually, let's just make it easier to read off for everyone. We'll just do this inverse. and zoom out. So this is probably going to go in an appendix. Yeah, so this is going to go in an appendix, but we will have to prove this in order to prove this theorem. I've proven it before, but what you can, if you would like, between now and either tomorrow or the next day, you can take a look at this and see, maybe if you have some time and energy, see if you can figure out how to prove this one on your own. It'd be a nice puzzle, I think. We're going to, as sort of maybe a hint, we're going to prove it by induction, but that's all I'll say. That we will prove that this particular constant is in A theta. But yes, so anyway, that would be all for today. Thank you so much for coming. It's been really fun. And it's really exciting that we're almost done. So we will probably be back to tomorrow or the next day, and we'll finish this off. If you have any questions, now is the time to ask. Okay. If not, then I'll see you later. Bye.